Hello, this is the first video of the second order differential equations series 1 on homogeneous equations for OCR Pure Core Further Mathematics. And this video introduces the auxiliary equation method by considering first order differential equations. In the series on first order differential equations, we looked at two methods for solving them: separating the variables and the use of integrating factors. We will be considering second-order linear differential equations with constant coefficients in this series. So a d2y by dx squared plus b dy by dx plus cy equals some function of x. For homogeneous, the function of x is 0. Note that the order n equals 2 is the highest derivative, the d2y by dx squared part. We call these linear differential equations because y and its derivatives are linear. In other words, those derivatives are not squared or cubed. A, b and c are constant coefficients. Before considering second-order equations, we will use the auxiliary equation method for first-order linear homogeneous differential equations of the form dy by dx plus ky equals 0. Previously, we solved these by separating the variable to give the general solution y equals ae to the minus kx. Knowing that this is the form of solution to any first-order equation of this type leads to an alternative method of solution which does not involve integration. We can use auxiliary equation method on first-order differential equations, and the other advantage is that it can be then extended to second-order differential equations and higher-order differential equations as well. Note that in general the solution of any first-order differential equation will contain this exponential function and just one unknown constant. Let's consider this example here. We know that the solution is going to be of the form y equals a e to the minus kx. Therefore, dy by dx would be of the form minus k a e to the minus kx. Let's substitute these ideas into the equation. It would give us minus 3k a e to the minus kx plus for 2y 2a e to the minus kx equal to 0. If we divide by a e to the minus kx, assuming that's not equal to 0, we would get an equation where minus 3k plus 2 equals 0, or k equals 2/3. And then we could then say that the solution, or general solution, was where y equals a e to the minus 2/3 of x. If we wanted to verify this, we could substitute that back into the original equation. This is called the auxiliary equation. And you will find that we often use the letter m in this auxiliary equation rather than k. As can be seen here. However, in some textbooks they may use another letter, for example the Greek letter lambda. So in summary then, for a first-order differential equation with constants a and b in the form a dy by dx plus by equal to 0, this being homogeneous equations, the auxiliary equation will be minus ak plus b equals 0, giving that k equals b over a, and then the general solution will be y equals ae to the minus kx equals ae to the minus b over a x, noting that there is no integration involved and we've used a standard result. This idea may be extended to second and higher order differential equations. In the next video, we apply this auxiliary equation method to second order differential equations.